Okay, welcome to leveraging NLP and deep learning for document recommendation in the cloud. This is a joint effort with Zoo, and thanks to them, but they are not here, so I will present everything. Here's what I'm going to cover today. First, I will talk about the job resume search challenge and opportunities that Zoo has. And then I will give an overview about the technology we are using, about the Analytic Zoo and the BigDL. Then we'll go details about the solution, then eventually takeaways. So Zoo is kind of, if I want to get a job, I go to Google, I could go Indeed, I can also go Jobs to Career. It was their own name, now it's called Zoo. So I type a keyword, then I expect some jobs come back. So Zoo is a job advertisement network. And actually these days, at a unique position in the industry. It's because they have thousands of marketplace partners. They have multiple channels to reach talent. They could go by emails, like sometimes job boards, job sites, sometimes search engine, even newspaper. So monthly, they have to process billions of queries, tens of billions of impressions, and tens of millions of interactions, and sometimes conversions. So they want to qualify the candidates. The current solution for them is by keyword search and match API. But jobs are rich content. Resumes are rich content. So jobs have like titles and content. But keywords, if you just go by keyword searching, it's pretty hard to work with. You probably end up with matching a specific keyword to a document that happens to contain that term. It will not recall if the document doesn't have that term. It works, but it has issues. There are plenty of ways to improve it. I will walk you through a couple of things, like stemming, like synonyms, like ontologies. It's important to know when and how they fail before go to the details of our solution. So first, stemming. There are words that have the same meaning with different suffixes. For example, if I want to go to a job like accountant, so I search a job accountant, would be enough to match an accounting job. The solution is chop it, then account and accountant match. But the problem comes out. But the problem is here. When you are searching for accountant job, you could be matched with accountant representative job. That's what we want. Another thing, synonyms. If the person, okay, so synonyms. If I am looking for a job like a registered nurse, so it's crystal clear to me, if I'm in this industry, that RN is a registered nurse for me. But the machine doesn't know. Then the solution for this is they create a map of synonyms to match. Then for each registered nurse, it has a synonym of RN. Again, it works, but the problem is it's manual process, and it takes time to make it right today, and it takes more time to make it right going forward. So another thing is for ontologies. For example, if I am looking for a job as a dishwasher, but the guy who posted the job might post like as different language. They say maybe they were posting a job like a back of house job. So the solution for this one is make another map for this restaurant industry, but thinking of how many industries are there. So you have many maps to maintain. So that's manual process, and it takes time consuming. It's a full-time job, actually. So another thing is for specifically suffering. Like for keywords, if I'm looking for a job for, let's say, big data, but specifically, which part of big data I'm looking for. So keywords here don't provide the full picture. Sometimes they are too specific. For example, if I'm looking for a Spark job, but I'm also might be interested into a job like BigDL or deep learning on Spark. So if we could provide richer form of input into the job recommendation problem, not just keywords, we can provide the full content. We will be able to find more matched candidates for jobs and more jobs for job seekers. So Tazoo has their existing pipelines running on the top of Databricks cloud using Spark. So they don't want to change anything of that, but they still want to leverage deep learning to provide better matches. That's where and why we started the collaboration. The technology is Analytic Zoo and BigDL. Here, I will give an overview about Analytic Zoo and BigDL and explain why it's a good fit for Tazoo. Okay. Intel is a primary contributor of open source technology, including Linux, Spark, Hadoop, so on and so forth. And BigDL and Analytic Zoo are recently open source projects for artificial intelligence. So BigDL is a distributed high-performance deep learning framework for Spark. And Analytic Zoo is on the top of that. It's pipelines and it builds applications. As you probably know, everybody knows here. So this is a Spark ecosystem. It becomes a unified big data analytics platform for big data engineers. So usually you have thousands of servers. You have massive data stored there, and data engineers are building applications, pipelines there. However, but for deep learning world, most of the times people are using different frameworks on different clusters. Then there's a challenge to move data. In reality, researchers work on research clusters, and the data engineers clean, transform data, copy the data from the data cluster to the research cluster. So there's a huge overhead. That's a gap we want to close. That's a gap we want to bridge, actually. So there's actually a fundamental incompatibility between the way the Spark scheduler works and all these distributed machine learning frameworks. There are many options to work on that. I will detail about ours here. So here comes to BigDL. We want to bridge the gap. We want to continue to use the familiar software tools and hardware infrastructure to build deep learning applications. And we want to analyze big data using deep learning on the same Hadoop cluster that the data are stored. Want to add deep learning functionalities to large-scale big data programs. So BigDL, bringing deep learning to big data platform, which means Spark ecosystem here. It's a distributed deep learning framework for Apache Spark. It's organically developed on the top of Spark. And all the programs of BigDL programs are just like standard Spark programs. You don't have to change anything. You just upload a jar which contains a BigDL to your cluster, and you can run it as any other BigDL, any other Spark programs. It achieves pretty high performance on CPU because it's powered by MCL, which is very fast. It's the fastest math library on Intel chips. Also, its efficiency scales out by leveraging Spark for distributed training and inference. Here, how it does the distributed training. So BigDL runs as standard Spark programs. You don't have to change anything on your Spark cluster. You just load the jar as you did. And at the training stage, we coalesce all the data, the training data, into numbers of workers that you have. And then each worker has a subset of data, which is your one partition. And then each worker gets a copy of the model. Then together is a bet. Then each Spark worker runs on the same model on a subset of the data. At the parameter synchronization stage, each gradient is divided into a couple of chunks. Then each worker is responsible for one chunk. Here, so the blue worker is a work one, is responsible to update the blue chunks of all the gradients, and the green ones does the green chunks. So that's why we get the parameter synchronization this way. So if you think BigDL is a framework, it has layers, criterions, optimizers, so on and so forth. So Analytic Zoo is on the top of that. It's a unified analytics and AI platform. There we have a lot of reference use cases. We have built-in deep learning models. We have feature engineering. We have high-level pipeline APIs. And here you can see it has a distributed TensorFlow and a Keras on Spark. It has native support for transfer learning, so on and so forth. At the backend, it's running Spark, TensorFlow, Keras, and BigDL. So here's how we do it. By building the end-to-end deep learning applications for big data, we support distributed TensorFlow on Spark. We support Keras style APIs, and we support NN frames, also feature engineering. To productionize deep learning applications for big data at scale, we support the model serving using OpenVelo powered. It's pretty fast. Also support web service like Spark, Storm, Flink, so on and so forth. For all the out-of-the-box solutions, we have a lot of built-in deep learning models. Then what can you do with Analytic Zoo? For example, you probably don't have a use case that's in your mind, but your use case might be specific enough. So there are some examples you can always check on our website. There are alarm detection, there are fraud detection, there are recommendation, there are sentiment analysis. A lot. Just check on our website from the apps you will see. To deploy and productionize our applications, we have been collaborating with a lot of customers. So our applications are building and running on a lot of platforms on AWS, on Azure, on IBM Cloud. And if you want to use BigDL and Analytic Zoo, but you have difficulty in that, you can contact with us, and we'll start from there from a POC, and we'll get eventually. Then that's a technology we are using, and I will detail the solution that we have now here. So the first step is for all the jobs and the resumes, they are just words. How do we present that in our solution? So the answer is we use word embeddings. So for each word or phrases from the vocabulary are just mapped to vectors of real numbers. The library we use is Global Vector. You can download it from the Stanford website. And at the backend, it uses a global log bilinear regression model for the unsupervised learning algorithm. The training is performed on aggregate data. It's by word-word occurrence stats from Wikipedia. In here, the vector representations showcase meaningful linear structure of the word vector space. For example, the accounting, so are very similar in the hyperspace now, but it's not that much similar to accountant representative. So that's why we got there. Then the model that we're using is Analytic Zoo recommender model. In the Zoo, we provide, now I think we have 3, including the neural collaborative filtering, wide and deep, and the sequence model. We answer questions using classification methodologies, and we can handle implicit feedback and explicit feedback, except all this predict or train functions and APIs. We provide 3 useful APIs for recommender for user, recommender for item, or predict user item pair. So here's the architecture of the NSF model. For each user or item, it's one hot vector. And on the top of that, it will learn a vector of this, we call it latent vector of the user or item. Then on the top of that, we build multiple layers. Then eventually, we output a score if it's a yes or no. So, but for our use cases, in here, we don't learn the user latent vector using one hot vector. We use the pre-trained embeddings of Glove. For all the documents, we tokenize, clean that, then each document is represented by one vector from the weighted mean of all the words in that. Together, we have this. Then the model details like this one. For resume Glove vector and the job Glove vectors, here we can use 50 dimensions or 100 or 300. And we just find out the simplest one, the 50 dimensions, good enough to present. Then these 2 latent vectors are concatenated. On the top of that, we build 3 layers in linear, and then the output is a log softmax. So that's a recommender model we do. It's pretty simple using our API. I mean, it's even simpler right now if we use the NCF model. Here, we just build it using the layers. So together, if we want to put everything into an end-to-end flow, it looks like this. We start from the raw data, and it has impressions for each document or each job, resume pair. It has a job ID, resume ID. It has a job content and resume content. And it also has a label. It's applied or it's just shown. Then if it's just shown without application, so that's negative. Then it's applied, that's positive. So together, we got all this data at 6 months, and we do the feature extraction, tokenize each document, and clean it. So for other documents, we got the weighted average of each document. Then each document, no matter it's a resume or it's a job, it's represented by a weighted average of the vector. It's just one, together I think it's 100. So each document has 50. Each pair has 100. Before it goes to the NCF model, we run a k-means for other users. That's because, for example, we group all these users into different clusters. We think maybe it's different because in the practice we found out it's very different for California users and for New York users. So in practice, we use 3 groups, and each group we build and trained one NCF model for that. And then when we have a test data, it goes through the k-means first. Then we find out which group these users become, and then we have an ensemble prediction for other users. So that's how we do this one. And we have a link here, and that's a blog published to that. For evaluation, this is the evaluation results from offline. What I found out is, here is the orange one are our NCF prediction, and the blue ones are the base prediction. That's by search. So compared to the control group, we can tell from no matter it's precision or MRR, our results are way better than the control group. So here, probably MRR is a ranking quality. That means no matter, even except the precision is better, but by the quality of ranking, it's even better. So this, the online, I think, the online evaluation, I didn't have a figure for that, but they just send the results, say it results in increase of thousands of dollars in revenue daily, actually. So that's the details of the solution. Then its takeaways. To work on this whole project, we just found out Analytic Zoo and BigDL integrates pretty well with existing AWS Databricks cloud. The ETL Spark, and Spark ETL and the machine learning platform, it's quite ready to be integrated with our library. Then our Analytic Zoo and BigDL scales with their data and the business, and it provides revenue increase. The jobs and the resumes or any document with rich content could be effectively modeled and processed through embeddings. This is pretty helpful. Also, the ensemble multiple models and global embedding vectors proved to be pretty effective for rich content. And more information you can always find on our website of the Analytic Zoo GitHub. Okay, thank you. Okay, question?
When you create a weighted average of your tokenized blood vector or blood vectors, how do you determine the weighting?
Oh, it's pretty, you're talking about here how we, so the question is, when we create the weighted average, each vector for each document, and how do we weight the mean, right? How do we get the mean? So the answer is just count how many words. And for each, it has the same weight. You mean how to handle the words? Sorry, I didn't get your question. Can you be louder? Oh, that's here. At the feature extraction step, we vectorize all the documents. The k-means runs after all the vectors, so you treat all the vectors as just features for this user. So for resume, you don't use other features, just use the vector as features. So you can just treat this one as features and you group it.